Hello, and welcome to Lecture 19 of AMAT502 at UAlbany. Today we're going to be talking about model validation and the bias-variance trade-off. Bias-variance trade-off is a really important topic in modern machine learning, which is still an area of active research. But before we get to that, let's do a quick roadmap of where we're going. So the topics for today, I'm going to outline the recommended reading from van der Plas, and then do a quick recap of the data science pipeline. This is going to lead us to the question of how do we choose a model and how do we know that model is a good choice? This goes underneath the heading of model validation. Here we're going to, again, draw into a sort of a philosophical comparison of what physics would say a good model is versus what data science would say is a good model. And then we'll get to the question of when the model is dictated by data science, how do we avoid things like underfitting and overfitting, which is one of the pitfalls of doing models purely based on what fits data. One way of measuring this is going to be R squared, which is the coefficient of determination. This will finally lead us to the bias-variance trade-off and the question of whether or not having more data is really better. We'll conclude with a case study in polynomial regression and a case study in k-nearest neighbors as applied to the iris data set, where we introduce our last topic of today, which is the KFold crossvalidation method. All right, so remember, we're often pulling a lot of the material from this portion of the course from Jake van der Plas's Data Science Handbook, which is an excellent read and available freely through his GitHub page here. We've been focusing a lot on Chapter 5, and Chapter 4 also includes lots of important information on plotting, which will be really relevant when you want to make nice, shiny presentations, which will be part of our final project. Today's lecture, we're mostly going to be following section 5.03 on hyperparameters and model validation. So I'd highly recommend that everyone also read van der Plas's Introduction to Scikit-learn, so we have a more formal understanding of what's called the API, this is the Application Programming Interface for Scikit-learn. Okay, so let's recap. We're interested in applying the data science pipeline. And again, a pipeline you just want to think of as a connection of pipes where every part has an important role in the transform from data to knowledge. What we first need to do is always choose a class of model. Are we going to be using regression or classification? Or are we interested in doing something that's more unsupervised, like clustering or dimensionality reduction? So whenever we want to create an object from one of these classes, and again, we mean this in the object-oriented sense of programming. We create an instance of that class and then do that by creating an object. And this object has attributes which are specific to the type of model that we're choosing. We'll see shortly what kind of attributes we're looking at. So then we have to do a little bit of pre-processing of our data. So we shape our data into a features matrix with a target vector. Again, this is sort of assuming that we're working inside of a supervised learning problem. We usually think of this matrix X, which is equivalently often given by a pandas data frame, where we have M rows and N columns. M tells you the number of samples, N tells you the number of features. And then we have some target vector Y for every sample, which indicates either the class that we're looking for or the value that we're looking for when we're doing regression. So when we've now taken all our data, often we need to take our instance of the model and apply one of these sort of fit functions like model.fit. So model here being an instance of whatever model class we're looking at. And then we're interested in actually predicting using our now tuned model, which goes in that whole train, model, predict paradigm of machine learning. Supervised learning, we want to predict these labels for unknown data by using this predict method. So we'll say like xfit equals, some linearly spaced array in NumPy, and then we'll see what the predicted y values are. This would be how we would plot, say, in regression. More often, we'll see in unsupervised learning issues of transform, such as when doing dimensionality reduction in PCA. So as a quick recall question, I want you to make sure that you could give me 2 examples of a supervised learning method and 2 examples of an unsupervised learning method. And then once you've chosen 2 from each of these classes of machine learning methods, I want you to go ahead and tell me, did we use the predict method or did we use the transform method when using Python? All right, so let's go through a simple example to just make sure that we really understand this pipeline. And we'll do the simplest model of all, which is regression. So I'm going to bring some plotting libraries, and again, I'm going to be creating some random noise where I have to instantiate it with some random state. I'll use 42 because it's such an auspicious number. All right. So let me go ahead and run that again. So what we have here in this example is essentially the line y equals 2x minus 1, but then where we've added some normally distributed random noise. And we do that across the number of points that we're generating here. So again, here we just let x be sort of random samples drawn between 0 and 1 with the uniform distribution. And then we scaled all that by 10 so that our x-axis lived between 0 and 10. And then for those 50 draws, we also created 50 draws of random noise, normally distributed. And then saw how this sort of noisy line looks. So obviously we have an underlying line that we could try to fit this to. It's 2x minus 1, but we're assuming that we're given noisy data. So let's see how we would do that in this case. So we have our x and our y. So x is our independent variable and y is a response variable. And we're clearly here in a regression task. All right, so we're choosing a model of by then importing the appropriate estimator class from scikit-learn. So let's see how we do that. All right, so we're looking in linear models. We can import the linear regression class. Okay, so we brought that into memory. Step 2, we need to choose model hyperparameters by instantiating this class with those attributes. So whenever we have a particular model, we think of there being these parameters which govern the model. You can think of this as sort of the actual values of the coefficients when we're fitting a polynomial. But they're also hyperparameters, and these are sort of higher parameters which govern things like the degree of the polynomial, or maybe things like should we force an intercept to be true. That's what's happening here. All right, so now model is our name of this linear regression object. So this is a class, and we've passed it these attributes. So think back to when we were doing our mortgage classes, when we were studying object-oriented programming. Okay, so we've got, now we need to arrange our data into sort of goes in the pre-processing step where we have some features and with some target. Okay, so X was just originally this NumPy array of random samples between 0 and 10. So we want to transform this into something that actually has this sort of these attributes. So remember what happens if we do x.shape. So notice it's 50 comma there. It doesn't think of itself as having this actual column. So this is just a peculiarity of NumPy. So now we've given it a new axis, and essentially by putting all this like so, we now have it turned into a column vector. All right, so now we fit the model to the data. So we literally just use the function fit, F-I-T, which is really a method that operates on this instance of our linear regression class called model. Okay, so right now we're just given some very generic instructions from Python about what's the deal with this model. And, we know things like, okay, the intercept is true, copy X true. All right, we didn't have anything about normalizing. Again, you should consult scikit-learn's documentation to really understand what each of these things mean. Okay, so now we get into how do we access some of the attributes of this model. And so notice there's this weird convention that for some models, when we want to access some of the attributes, we have to take the attribute name, which includes an underscore. So for example, model that coefficient is telling us the slope of the line. Remember, the true slope of the line was 2, and the estimated model coefficient was 1.97. So we're pretty close. Now let's get model intercept. Yeah, -9. So get pretty close to what the true y-intercept should be, because remember our equation looked for y equals 2x minus 1. Minus 1 would be the true y-intercept, and here we're seeing it's minus 0.9. Okay, so I just want to make a quick comment on this underscore annotation. So you'll see this in a lot of ways. So when we're doing object-oriented programming, we have this double leading and double underscore, sometimes called a dunder. And that was invokes some sort of special conventions within Python that knows that we're going to be working with a class as being defined by you, the programmer. There are other instances where you need to use this sort of underscore. If you have sort of this leading double, usually that means we want to do something called encapsulation. If we're trying to hide methods or attributes which shouldn't be inherited by subclasses. According to this article, and from what I've been able to find, just having a single trailing underscore is just a naming convention to avoid conflicts with maybe things that other people have written. And so for whatever reason, scikit-learn's linear regression model has decided to use this name with this trailing underscore. So just think of it as a convention. Okay. All right, so again, we've created an instance of our model. We've transformed it into this X viewed as a matrix. Here we're really a column vector. Y is the predicted values. Now we want to actually make some predictions. So how do we do that? So when we're doing regression, we're essentially creating new test data by just creating a linearly spaced array. In this case, from -1 to 11. And so now we reshape it so that this now looks like some test samples. So again, now this basically turns it into a column vector. This is just an array. Now this is a matrix, but with one column. And so now we want to see when we predict values when fed this capital X fit, not the lowercase x fit. That's going to produce for us essentially by taking in whatever entry in that matrix is, and then take it times look like 1.97 minus 0.9 something. And so now we can plot all this. So we can see here that we get a line, which actually looks pretty nice. So we have our original data, it's our scatter plot x, y. Now we're plotting x fit, y fit. Notice that we ended up using the original sort of NumPy array. So just be mindful that sometimes you might need to transform your test data so that you can actually fit it to your parameters. And that will then output another NumPy array. But then for plotting purposes, perhaps you need to use the original NumPy array. So just out of curiosity, let's see what happens if we try to use capital X fit. So this actually works fine too. So either one worked. All right. Put it back here. Okay. All right, so that was a quick recap of the data science pipeline using scikit-learn's API in the specific example of linear regression. There's more than I can go over in a single class, and it'd be honestly boring for me just to go through all those things. See, this is where you really need to take ownership, get in and investigate some of these particular models and just try it using whatever example data sets that you can find on Kaggle or these other websites. So let's take a moment and step back and think about, again, what are some of the differences when we're talking about models and data? And how does this notion of model in data science compare with models as we've been using them, at least among scientists and engineers, for hundreds of years? And I want to really boil this down into a question. And this question is essentially, when I choose a model, how do I know it's a good model? So it used to be the case, if we think back to sort of Newton and some of these original scientists, that he posited this law of universal gravitation, that all objects attracted each other. So here he posited that there was this causal mechanism which drew objects together just by the fact that sort of mass can create attraction. And so he even gave a mathematical equation for how strong this force of attraction should be, which used this sort of 1 over the distance squared as a sort of the proportion for determining how attracted two objects were. And from this, he was able to model and create these sort of elliptic solutions for the planets. And that turned out to be a really, really good model for how the planets moved. In some sense, this was like the pioneering and like the way of thinking about modeling and discovery for hundreds of years. But in data science, we're in a different situation. And so it's one of these things where we almost become a little Aristotelian, or I should say even going back to, I believe it was Kepler who actually believed in these sort of epicycles. But however that goes, the point is we in the past used to come up with causal explanations. Objects were attracted via their mass. And then we were able to produce a mathematical equation. And then when that mathematical equation seemed to fit data, well, first of all, not only did we believe that the model was principled, we also had the good advantage that when it fit the data, we're like, this is actually making good predictions. Alternatively, we could just take a data first perspective. And this is more and more likely what's happening today, where we can often collect data that's observed about systems where it's hard to deduce simple principles. So there what we're trying to do is we're prioritizing fitting the data above anything else, including conceptual simplicity. So as I was just saying, reason one, why we want we think one model is better than another's. Think of this as being in the realm of physics. One uses basic physical laws and then solves equations like Newton's equations or Schrodinger's equation. And then this gives us whatever our specific thing that we're trying to model. But this sort of principle is completely useless in sort of topics that are very pertinent to us today, such as suppose we're interested in how people are going to vote. And maybe we're interested in the question of, depending on where a person lives, how does this dictate their vote? And we might be interested in, say, what's the difference between rural versus urban and its influence on people's voting preferences. So this is a sort of situation where data science excels and sort of ordinary science or causal science has nothing to offer. In particular, you might ask, is it the case that you can write down physical laws to dictate what is a person going to do when they go to the ballot box? Unless you have some very, very strong, opinions about how humans are influenced. You might say that, no, there's no way we can actually predict with 100% accuracy what someone's going to vote as, just depending on where they live. After all, we believe in notions of free will. And so in that sense, we don't want to think of there being physical laws which govern thoughts. But nevertheless, it has been observed empirically. And if you click on this link, this will take you to this Pew Research article, and you'll see that, amongst rural and suburban counties, well, rural tends to definitely trend Republican, and less so Democratic. And then you see the flip when it goes to urban. So urban environments tend to be heavily Democratic and not as much Republican. And then suburban, sort of an even split. So here we've observed empirically that there seems to be this trend. And you could try to ask, how do I model or predict how a person's going to vote? So you might actually have a lot of success in terms of machine learning methods if you use something like k-nearest neighbors. And if you just ask, like, what do my neighbors vote as? Does that influence or predict how I'm going to vote? There's a good chance that it actually does. But again, it's not necessarily, you might ask yourself, is this really a causal model? Or is it just purely correlative? Which gets into the question of what's the difference between causation and correlation. Okay. So the point is that there are plenty of very interesting data science tasks where we wouldn't want to write down fundamental laws of physics to try to begin our modeling task. We'd not want to write down Newton's laws or Schrodinger's laws to start figuring out how someone was going to vote. But instead, I could try to use maybe other machine learning methods to just focus on getting what's the most accurate predictor. So that's the real question here, is how do we come up with models that are the most accurate at prediction? And should that really be our guiding light? After all, if our models seem to fit the data best, what makes them any worse than models that are supposedly principled based on sort of physics or something like that? Well, here's one word of caution. So we've already seen examples where just fitting the data is not good enough, because we have good mathematical reasons to know that, for example, by Lagrange's interpolation formula, that we can always find a model that perfectly captures observed data. If I give you this sort of scatter plot of points, I can find a curve, although not this one, that goes through every single point. Of course, I'll need a degree of a polynomial equal to the number of points that I have. And so then that just gets to a question of, all right, that's a clear instance where I've overfit my model, or I've overfit my data, made my model just try to fit things. And the question is, how do I quantify whether or not I've overfit? We're going to get to that very shortly, but I want you to just take a quick look at what we've got here. So here's an example of some data, the blue scatter plot points. And then if we were to just be very lazy, try to use linear regression like we just used, you could see that, all right, this model's not really doing what we want it to do. So this is an example of underfitting data. We also call this a saying high bias. It's a very biased model. But over here, we've got one which overfits the data. And this is sometimes called high variance. And so this gets at what's called the Bias-Variance Tradeoff. But when just looking at these polynomials, you might ask yourself, what are the degrees of each of these? Obviously, this is just a line, so it's a degree 1 polynomial. How might you go about determining the degree of this polynomial? Well, if you look at it carefully, you know that one way you can estimate degree, if you remember your calculus, is you can ask, how many max and min does it have? And that's going to tell you something about the degree of the polynomial. So you could just start counting. There's a max, there's a min, there's a max, there's a min. And just by counting these, you know that you're actually getting zeros of the derivative. And the derivative is just 1 degree lower of polynomial than the original polynomial. So I leave it to you to go through and try to estimate that for yourself. Okay, so let's try to get at the question of how do we determine, obviously we want an accurate model. I mean, we might say that that's our holy grails, the most accurate model possible. But we also want to safeguard ourselves from having a high variance model, one that overfits the data. So one way in which we can do this is using, again, this sort of train test split. We'll get in again to the Python specifics of how we do that. But the key thing to do is, what we want to do is split our data. And then we have some X train, some X tests, and then we can use the test to generate new samples, or we can use synthetic examples like we did with regression. And so one thing we can note is that even if we overfit our model on training data, we can use the test to determine just how much we've overfit. And let's look at how one metric for measuring overfitting. And so this gives us a way of validating models just by doing sort of a reserve. We have some train and then we have some testing data that allows us to validate models without using physical laws. Because again, we don't believe there are going to be physical laws that predict how someone's going to vote. So let's do a quick summary of R squared. This is our coefficient of determination. So R squared is defined to be 1 minus the sum of squared residuals divided by the total sum of squares, which is defined actually using the variance. So this is we're taking each observation, we're subtracting the mean of all those observed values. And this essentially would be the variance of our data if there was no dependence on y by x. So here, if we just had something that was sort of, you can think of this as being the errors assuming a null model. So basically deviation about the x-axis. When I square all that, that's going to be my S total. Now, of course, as we used earlier, when we first introduced regression, we can come up with some function and we can evaluate that function on each of our test samples or even our training samples. And that's going to give us a predicted value, fi. And then we can look at the difference from the actual value. We can square that, and this will give us our sum of squared residuals, where again, this depends on our choice of model, which we're using to predict values. So this is just variance, S tot, and this is the sum of square residuals, SS res. And so if I look at the ratio of those two, again, both these numbers have to be positive, and I divide them and I take 1 minus this. This gives me some notion of how good my model is. So let's look at the two ones we just looked at. So here was an example where we've reserved our data into train and test portions. Train is going to be blue points, test is going to be red points. And so for each of these, we can perform the calculation for R squared. So you'll notice that with training on the blue points, and I make this line, so obviously there's a lot of variation, but then I look at the sum of variance as it deviates about this line. Now I take 1 minus that ratio, I get 0.7. So it's not a great predictor, but it's at least something. Notice in particular it's positive, and pretty close to 1, but not as close as we'd like. Funnily enough, when we validate, so we do this model validation step on our test data, we actually get a slightly higher value of R squared, which again means that the performance of this model on both the train and test data is about the same. Now, if we look at this example where we use a high degree polynomial, one where we think we've overfit the data, because we've chosen this high degree polynomial, it very closely tracks a lot of blue points. And so as a consequence, essentially nearly all of the variance in the model is minimized. So meaning the deviation from these blue points from this curve are very small, especially when viewed as divided by the total variance that's just going above the y-axis, deviation from the line y equals 0. And so in that case, they got a very low variance when measured against the predicted model. So then 1 dominates, and then so 1 minus a small number is going to be something that's close to 1, and that's why we get 0.98. So traditionally, we think of this as a great prediction. But when we then reveal our red points without allowing our curve to update, you notice that this huge, move that it made so that it could go up and then come back down for these blue points, that's going to incur a really high error. And so by comparison, and in fact, the errors are going to dominate so much that you're going to have 1 minus a really large negative number. And so that's why we have 1.8 times 10 to the 9th. So that's in the billions nearly. So that's a very, very large negative validation score. And our goal is to have something that's very large positive, but in fact, it's always going to be bounded by 1. So something close to 1 is good, something that's close to 0 is bad, and something that's very, very negative is even worse. All right, so this is our validation score tells us that maybe we overfit our data. All right, so this gives us to one of these principles called the Bias-Variance Tradeoff. So for high bias models, so these are models that underfit the data, the performance of the model on the validation set is similar to the performance on the training set. We saw that in the first example over here. 0.7 and 0.74 were pretty close. Now, on the other hand, when we look at these sort of overfit models, we think of this as high variance, the performance of the model on the validation set is far worse than the performance on the training set. So even though by allowing ourselves to have a high degree polynomial, we look like we are really explaining the data well, but not so well actually, because by the time we had to test this model against new data, it performed much, much worse. So this told us that this high variance model was, the variance was between the performance on the training set and on the testing set. So we've got a picture that sort of summarizes all of this. So again, this has been color coded. So we can think of this as the validation curve. And so the idea here is that, there are these hyperparameters that govern some of these models, like in, if we look at, say, regression, we can look at the degree of the polynomial. We think of higher degree polynomials as more complex. So that would be a variable we could toggle. And again, Lagrange's interpolation theorem tells us that if we go arbitrarily far this way, we can maximize our training score and make it as good as we like. And then for another example of something that's a model complexity parameter, we might try to use either PCA, the number of dimensions, or maybe we could even look at the number of neighbors that we look at when we're doing KNN. Anyhow, so we always train on our blue data sets. And so as we increase model complexity, generally speaking, we can always improve our training score. But when we go to test, we'll often see that there's some local maximum. And the guiding principle that we use in data science, especially when we don't have physics to validate our choice of model, we say that the best model is one that sort of maximizes the validation score, because that means given new data, we're doing our best job at predicting. And so that tends to lie somewhere in the middle. So keep this in mind. All right, so now let's go through another example, again, following a presentation in van der Plas. All right, so again, we're gonna have this make pipeline, which is gonna combine multiple features. And again, the way that we usually work this is we actually think of polynomial or higher degree regression as being an instance of linear regression, but after we've transformed our basis functions to then be one that goes like x squared, x cubed, et cetera, and then we do linear regression on this transformed data on this higher dimensional space. All right, so just brought that into memory. And right now we'll focus on the issue of degree equals 2. So that's really indicating our transform. All right, so now let's look at a synthetic example as presented to us by van der Plas. All right, so make data. So we have this function make data, where n something, error something, and then we've got some random seed. Again, these are all given default values, so we don't need to always specify what error in our seed is going to be. But let's just read the code here. So we're going to create some random object with this random seed. And then we're going to generate some random numbers. We're going to square them. And then we're going to look at y, which is going to be 10 minus 1 over x, where we've applied this Ravel method, which essentially has the effect of sort of flattening and turning our sort of whatever array of data where we've taken n draws and flattening it and turning into a nicely behaved NumPy array. We've done this plus 0.1. So notice we're dividing something. So 10 minus 1 over x plus 0.1. And so we've noticed x, if we read this code correctly, these tend to be random numbers, but then we've also squared it. So this should be always a positive number. And then we've got also this error function here, which then says if, which essentially bounds how far our error is. And this makes sure that we can transform or scale our error in the appropriate way. All right, so let's see how this works. So we just brought in, this returns a list or a tuple here, x, y. And let's go ahead and look at what this looks like. So, all right, cool. So you want to think of make data as, we've already generated x, y. These are our black points here. And what we're looking at here is various degree polynomials that have been fit this data. And so here what we've done is we've written a for loop that iterates through a degree 1, that's going to be our line here, degree 3, and a degree 5 curve. So one question I have for you is, what do you think is the best degree polynomial for fitting this data? And just given what you know about what that function should be, and sort of just go back and look at it. 10 minus 1 over x plus 0.1. What do you think is sort of the optimal data here? And so, and again, just thinking about that, you can ask yourself, well, would any polynomial actually be a good fit for this? All right, so setting those questions aside momentarily, we can go ahead and try to perform this sort of bias-variance trade-off. We're going to use this by actually using Python's validation curve function. So you can see that there is actually a part of the model selection library in scikit-learn that allows us to do this validation curve. And we're going to get into explaining what each of these things do, in particular what this CV equals 7 means later. But let's go ahead and try to plot each of these things. Okay, so this is wonderful. So what's happening here, if you read this code, is degree is stepping through between 0 and 20. We're going to think of these as the different degrees of polynomials that we're allowing ourselves to try to fit that data. And so this gives us our model complexity. And we then can track with the blue curve to see what is our training score for these increasingly complex models. And as predicted by that schematic we already showed, as we let the complexity become large, our training generally improves. But our validation score, again, has kind of this bow shape that indicates that for some somewhat low degree polynomial, we actually got really good prediction, and things just sort of tailed off as we went higher and higher. So let's just go ahead and try to get into what's happening here a little bit more. So notice that these train scores and validation scores are being produced as the outputs of this validation curve function. And so I'll leave it to you to read the scikit-learn documentation to see how this works in greater detail. But so one thing we just observed there is that, again, let's just step back through. So we tried 20 different degrees on our polynomial, but then our data was actually, so we made data with 40 points, 40 observations. So what happens if we just generate more data? We'll get to an interesting point that sometimes more data isn't always better. And in fact, if we want to allow ourselves to train on more and more data, there's this generic phenomenon that the validation curve tends to actually approach the training curve. And so our learning curve is then one which basically documents that as we train more, we're going to be able to test better. But we've also been able to obscure the benefit of sort of simple models, ones that maximize the validation curve, because again, the training curve just tends to go up. So let's see how this actually happens in the example as executed by van der Plas. So, so he's calling this make data function again, but now instead of 40 points, we're going to make 200 points. And again, we have to do this thing where we flatten and return this contiguous array. So now we see that there was just a few black points which sort of trended along this curve, which again, remember, this looks something like 10 minus 1 over x plus 0.1. You can see that there is, again, that 1 over x should have you concerned that this is going to be something that sort of blows up as x goes to 0. Again, we're protected from that because we've squared numbers and we've also got this offset from 0 given by that plus 0.1. But either way, we have a bunch more data now, and let's try to run through the same validation curve example in Python. So and you'll see the moral already is that more data means that there's no clear model winner. So when we plot this validation curve, which again is being plotted against the degree of the polynomial, there's no clear local maximum like happened when we had with our 40 points. So below we have this 40 points dash, and the plot for 200 points is going to be in bold. So let's see what this looked like. Yes, very good. So we had dashed was our 40 points example, and you saw there's clear outperformance as the model increased complexity, but then the validation curve sort of hit this peak and then quickly dropped down, which would have told us that with just 40 points, 40 observations, that maybe degree 3 or 5 polynomial was fine. But now once we allow ourselves to work with 200 points, we do the same thing. Again, we populate a degree NumPy array, which goes from 0 to 20. We go through the same sort of validation curve functions. And again, you can use this and fiddle with the example to see what happens. We got our original one, and now our val score 2 and our train score 2, which they plot for every one of these degrees. Let's notice we're applying this polynomial regression class, and what we're doing is we're doing it for each one in this degree, and the validation curve understands how to handle all these parameters. So again, understanding the mechanics of how this function works is going to be really important. But nevertheless, we see here objectively that by increasing our number of points in our training and testing, those curves end up sort of merging. And so this is meant to give you an example of how more data sort of maybe makes deciding on a simple model winner not so clear. But I ask you this question, which is van der Plas's example actually a good one? So if you think carefully about what does it mean to write down a polynomial expansion of the function 10 minus 1 over x squared plus 0.1? I actually see that there is no finite degree polynomial that perfectly captures that. So said in different words, if I went through Taylor's approximation, would never actually run out of higher degree polynomials that improve this model. So in some sense, having more data has actually taught us something, which is that the curve that we're sampling from is not a polynomial. And in fact, to model it with a polynomial requires arbitrary high degree, which actually tends to indicate that, at least in this setting, more data is better. And it led us to the belief that higher degree polynomials are accurately describing this data. because unfortunately our class of models, which is constrained to look at polynomials, is never going to be able to describe the function 1 over x squared plus 1. All right, so that was an interesting sort of math example, which both illustrated the principles or concepts of this bias-variance trade-off, and also this convergence of validation curve and the training curve when we took in more data points. Although maybe just by choice of the model, we knew it was going to have that convergence behavior because actually this was data that was not accurately modeled using a polynomial. But let's go ahead and look at sort of a more general process for what are ways in which we can validate on data, especially when we don't have just a make data function that allows us to generate arbitrary number of samples from this model. So let's see how this works, and let's first show how you do things sort of the wrong way. So this is where we're going to look at the iris data set, use KNN, and we're going to not do any holdout sets. So we're going to go through, and again, here we're just going to make use of the fact that their scikit-learn already has built in this iris data set, and we could just literally write load iris. So if I did look at the k nearest neighbors classifier, and notice here I've specified the hyperparameter that the number of neighbors is just going to be 1. If I try to do this whole fit and predict pipeline, I end up getting actually a performance of 100%. What happens if I change this model a little bit? All right, so 2, 3.96, 4. So all these things were slightly lower, but still, when we did it with 1, we had 100% accuracy. The reason for this is that actually, when we're going through and we're predicting on the full data set, that means that when I go to a point and I ask, all right, what's your nearest neighbor? In this case, I'm sort of testing on a point that was already in our training set. And so normally when I test, I go for the nearest point in the training set, and then I use its value with n neighbors equals 1 to predict this other point's value. But here, our training set is equal to our testing set. And so when I pick a point and I ask, all right, let me go to its nearest neighbor, it just goes to itself. And so of course you're going to predict it with 100% accuracy because you just looked at your own class label's value. So this illustrated a couple problems. One, we used a very low number of neighbors, but 2, we didn't actually perform this train test split. So let's see how we do that. All right, so again, this is a part of the model selection library. There's this train test split function. So I'll just make a note that Van der Plas used this older cross-validation function, which has been deprecated. But all right, so in this setting, what we do is we use this train test split, and what it does is it, again, seeded with random state 0, is it now picks half the points to go into one data set and half the points to go into the other data set, one for training and the other for testing. So what we do is we fit on x1 and y1, and then when we want to actually predict, we can use the other data, x2, to predict. And here I got my predicted as being the thing that comes from y2 model. That's just the variable name I assigned to the predictions associated with those x2s. And then I can compare how accurate was this compared with the actual values for y2. And here you got, using, again, model as having only one neighbor that it looks at, 90%. So of course you could go through and change the number of neighbors, and this leads to things like the elbow method to figure out what's the best way of choosing k. Anyways, by doing a 50-50 split, looking at only one neighbor, we were able to get a 90% accuracy still. So that feels much more reasonable. Here's another option. And again, when you have sort of hyperparameters that you want to vary or toggle, it's really useful to be able to test multiple times. And we all know that gathering data can be expensive. We often fund experiments with millions, if not billions of dollars to gather new data. So sometimes it's good to just make the most out of what data we have. So one example of this is we could separate our data into two halves, train on one, test on the other half, but then also train on that other half and test on the first half. So suppose I do this thing where I take my model, I fit it using X1, Y1, and then I predict it on X2. I think this would be my Y2 model. But then I could have also fit it on X2, Y2, and then predict on X1 to then get the values from there. Now I can compute two different accuracy scores. You can see that actually in this other one, I get 96% accuracy and then 90% here. So which one's the true accuracy? Again, we just randomly divided our data and then did this thing where we trained on one and then tested on the other. And then that gave us an accuracy score of, let's say, 90%. And then we reversed those roles. And actually for that setup, we ended up having a 96% accuracy. And so what is the true accuracy of this method with this parameter, hyperparameter, where the number of neighbors is 1? Maybe you should take the average of these two numbers. Again, there's some element of randomness here, so you can always do things like take the expected accuracy. So this leads us actually to a more general idea. Instead of just splitting in half and then training on one, testing on the other, and then flipping those roles, we can actually do something that's called KFold Crossvalidation. The basic idea here is take your training data, and you're going to reserve your testing data for the very, very last bit of testing, because you don't want to sort of spoil or bias yourself too soon. So you can take your training data and you can divide it into K subsets, again, of roughly equal size. And then you can take K minus 1 of those subsets, train on those, and then test on that last one. And you can now step through which one is the one I hold out. And this gives us this sort of diagonal of folds where we trained on the last 4 and we tested on the first fold, or in this next split, we train on fold 1, 3, 4, and 5 and test in fold 2, and so on and so forth. This means with our same training data, we can actually get a lot more tests out, get a better sense of what's the variation in accuracy scores. And then we can do some final tests on our actual test data. And again, this is all done, again, using this now cross-val score function. And here I set the number of folds to be 5. Remember earlier we did this 7 thing. And indeed now we get 5 numbers. And remember before we got this like 90%, 90.6, and then 96. And so that would have given us 1 average. But now when we go through this, we see, we get 2 96% accuracy folds, 2 93%, and actually 1 100% accuracy fold. But we could also up this to 10 folds and get a broader sense. Now, unfortunately, with the iris data set, it's relatively small. So you're getting sort of more likely to get 100% accuracy when you're holding out smaller things to test on inside your training set. But nevertheless, this is a very useful method, and I encourage you guys to use ideas from cross-validation when you work on your final projects. All right, so that's all, and I look forward to seeing you in class soon.